Welcome to the module that will guide you through the mastery of ice preparation. Perfect ice and its hardness are not an accident, but the result of a precise orchestration of 5 physical variables. Our hardness index on a scale of 0 to 10 depends on ice surface temperature at 45%, relative air humidity at 25%, water quality at 15%, air temperature at 10%, and ice thickness at 5%. Any deviation from the optimum results in player complaints or thousands of euros wasted by overworked compressors. Let's look at the charts individually.
The charts show that the optimal ice surface temperature range is around -4.3 degrees Celsius, where the hardness index reaches ideal values. Physically, the pre-melting phenomenon is at play here. At temperatures approaching 0 degrees Celsius, a microscopic layer of water forms on the surface. The colder the ice, the harder the surface, and the faster the glide. A major problem is blindly overcooling the concrete slab, where the surface might reach -7 degrees Celsius instead of -4.3 degrees Celsius. The ice then becomes brittle and chips. Every 1 degree Celsius of unnecessary overcooling increases energy consumption by 5 to 7%. On a typical league stadium, overcooling by just 2 degrees can cost you up to 17,600 euros annually in wasted electricity without any benefit to the players.
The chart reveals a critical dependency. Ideal humidity is around 47.5%, where hardness is at its peak. If humidity rises above 55%, a microfilm of condensation forms on the ice, making it soft and heavy. Conversely, humidity below 35% triggers sublimation erosion, causing the ice to lose mass. Ignoring the dew point forces the cooling system to work at maximum capacity to constantly freeze the excess moisture. This humidity barrier can cause a drop in cooling efficiency of up to 20%. The absence of dehumidification, compensated by compressors, results in average losses of 6,000 to 21,000 euros per season.
It is clear from the chart that the lower the TDS, or total dissolved solids, the harder the ice. Pure water freezes faster and forms a rigid lattice. High TDS, such as calcium and magnesium, disrupts these bonds, resulting in porous, white ice full of insulating air pockets. This porous ice acts as an insulator. The BMS system must lower the glycol temperature by 1 to 2 degrees just to maintain the surface. This poor thermal conductivity can increase the cooling load by up to 10%. Freezing low-quality water essentially acts as a hidden tax, costing up to 10,500 euros annually. This graph illustrates the slight but significant decrease in hardness as air temperature increases. Warm and humid air above the ice heats the surface through convection and radiation, softening it regardless of the cooling power in the concrete. Poorly configured HVAC systems that blow warm air directly onto the ice surface instead of the grandstands reduce cooling efficiency by 5 to 10%. This tug-of-war between arena heating and slab cooling can burn hundreds of euros monthly. The hardness curve here is uncompromising. The ideal thickness is 35 millimeters. Thin ice under 25 millimeters is fragile, while thick ice over 40 millimeters acts as a perfect thermal insulator, much like polystyrene. The cooling power cannot penetrate upward through it. This creates a massive thermal efficiency gap, or delta T. For example, the surface is at -2 degrees Celsius, but you are forced to cool the concrete down to -10 degrees Celsius. If the resurfacer applies more water than it shaves off, the thickness grows. Every 1 millimeter of ice over 30 millimeters represents a 4% increase in energy consumption. An arena with 45 millimeters ice instead of 30 millimeters can waste up to 31,700 euros annually just due to blocked heat transfer. Here, physics translates into pure economics. Let's summarize the hidden costs of poor control systems, or BMS, settings. First, excessive thickness.
Having 10 millimeters more ice than necessary costs approximately 31,700 euros annually in wasted electricity. Second, ignoring the dew point. If the system doesn't react to humidity and must constantly freeze atmospheric moisture, you lose about 21,000 euros per season. And third, blind cooling. A classic cool it just to be safe approach, where compressors run overnight without predicting actual needs, brings an additional loss of roughly 9,000 euros. In total, we're looking at a savings potential of up to 61,700 euros per year for a league arena. Beyond the money, optimization dramatically improves the ice quality for the players.
On this slide, we look at two phenomena invisible to the naked eye, but immediately felt by your wallet and compressors. First, healthy versus degraded ice. On the left, healthy ice has a minimal delta T. If the surface is -4 degrees Celsius and the slab is -6 degrees Celsius, the cold flows smoothly. On the right, degraded ice has a massive delta T. The surface is -2 degrees Celsius, but you must cool the slab to -10 degrees Celsius. This is because a thick or porous layer blocks the cold from reaching the skater. Next is the dew point. This is the physical breaking point. It's the moment when the air in the arena can no longer hold moisture and literally drops it onto your ice. The results are micropuddles, dull skates, white fog, and instantaneous compressor overload.
How do you achieve top-tier ice? It depends on your path to perfection. The gold standard relies on HVAC and RO filtration. You use demineralized RO water with a TDS below 20 ppm, which freezes crystal clear and allows you to set the glycol 1 degree warmer. The HVAC system strictly maintains humidity between 45 and 50%, keeping the dew point safely off the ice. The resurfacer then applies only a thin film of water at 60 degrees Celsius for instant layer bonding. Alternatively, there is the Gorilla mode for arenas with no HVAC or RO. Here, you apply extremely hot water, 75 degrees Celsius and above, from the resurfacer to naturally degas the water, compensating for the lack of RO. Humidity is managed by manual extraction from the corners and nighttime microventilation. This mode requires rigorous control, regular deep shaving is necessary, and thickness must never exceed 30 to 35 millimeters.
Today, we no longer wait for the ice to degrade or for the electricity bill to arrive. We are moving from reaction to prediction. The first step is smart data collection, which means the end of paper logs. Electronic ice forms send data straight to the cloud with zero latency. The system then analyzes the situation in real time, instantly calculating the hardness index and thermal efficiency. The proactive AI engine doesn't wait for the ice to fail. It warns you early. For example, it might report, "Tomorrow will be +15 degrees Celsius with 60% humidity. Lower the glycol and turn on the HVAC tonight, or the ice will go soft by 2 p.m. tomorrow."
To bring the ice quality in your arena into the 21st century, we have prepared this action playbook with concrete steps. For immediate action tomorrow, measure ice thickness across 14 zones, ruthlessly shave down anything over 38 millimeters, and audit the capacity and filters of your water softeners and dehumidifiers. For BMS optimization within 30 days, program alarms for the dew point value, reduce the volume of water applied during resurfacing by 15 to 20%, and calibrate concrete slab sensors against the actual ice surface. Finally, for strategic investments next season, deploy digital data collection and AI reporting, and consider a reverse osmosis water treatment system. Remember, the investment pays for itself entirely from the savings on wasted electricity.